Last test review problem. Number 8 is the randomization distributions. So to see whether a program of special stepping and foot placing exercises for 12 minutes each day could speed up the process of babies learning to walk, 12 baby boys were randomly assigned to the special exercise group or to the exercise control group. For the control group, parents were told to make sure their infant sons exercised at least 12 minutes per day, but they were given no special exercises to use and no other instructions about exercise. The data measured the age in months when the baby learned to walk without help. The mean walking time for the regular exercise group was 1.25 months longer than the special exercise group. To determine if this difference was statistically significant, the evaluators performed 1,000 randomization trial runs and created the distribution below. All right, so that's a lot of information to process. That's one of the things about these is that if you're talking about experiments and the numbers involved in analyzing them, you need a lot of information, right? So we can see that there are 2 control groups here, right? There's a special exercise group, and then there's an exercise control group. There were 12 baby boys, so that's sufficient number of subjects, and they were randomly assigned, right? So the control group did their exercises 12 minutes per day. The special exercise group did theirs for 12 minutes a day. And when the study was done, the data measured the age in months when the baby started to learn to walk without help. That was the response variable, right? When did the baby start to learn to walk without help? So they're trying to see if these exercises helped babies walk sooner. So there's the response variable. The baby boys were the subjects. So that's not part of this question, but it's the kind of thing that will come up on the test. So you might as well be able to practice that here and understand what happened. All right, so the mean walking time for the regular exercise group was 1.25 months longer. Okay, so it took that regular exercise group longer to learn to walk by 1.25 months. So that suggests that the special exercises were good, but that those special exercises maybe helped those other babies learn to walk sooner. However, we don't really know if that's statistically significant or not. So the statisticians, the evaluators, performed the randomization trials, right? So question A, how did the evaluators create one run for this distribution? So this is the kind of question, right, where we talk about how did they behind the scenes, right? This is 1,000 trial runs. So think back to what we did in class when we created our own randomization distribution. We took all of the data from our experiment, we shuffled it, we put it into 2 piles randomly, we took the mean of each group, and we subtracted them, right? And that gave us a mean difference that we knew was created by chance, that we could then compare to this one that we knew was created by the experiment. So, what are the 4 steps? Shuffle the original data, divide it into 2 piles, find the mean of each pile, find the difference of the means. So that's what you write here. And those steps are in your notes. They're just something you have to have memorized. So if you have this, there's 2 questions on this test that if you just have memorized, you'll get perfect grade on those parts. This part, and then question number 2, right? So just memorize those and you're guaranteed 2 questions perfect. All right, now this one is just a question if you understand reading the histogram. What does the bar labeled 58 at the top represent? So here, this bar labeled 58, what does it represent? It represents the number of random trials with a mean difference between 1.5 and 2.0, right? So this is how many trials had a mean difference that fell between those 2 points, right? So write that down. 58 is the number of randomization trials with a mean difference between 1.5 and 2.0. Technically, it doesn't include 2.0. It's just up to 2.0. 2.0 is in this group. All right. What percent of the random data had a mean difference that was as or more extreme than the difference for the actual data. So now this is getting into using the information, right? That's us calculating. So here is the actual data, right? Negative 1.25, right? And remember, we need to plot that on the positive and negative side. So they already plotted it on the negative side. We need to plot it on the positive side as well, right? So here it is on the negative side. Here it is on the positive side. The question is, what percent of the random data had a mean difference? So remember, all of these are mean differences, but that were as or more extreme than the difference for the actual data. So we want to know how many of the randomization trials fell outside of this, and then we want to convert that to a percent. So I plotted this. These are those steps. I plotted on either side. Now I need to count up the numbers in the bars, right? But the problem is, notice, this one got cut in half, right? So if you think about it, there's not 103 on this side. I just have to guess that it's about half. Some guess that there's like 51 on this side. And here, there's not 117 on this side. I'm gonna guess it's about half. So this is estimating, given that we don't know the actual number that's on this side. So half of 100 and, let's say 18, we're gonna round that to 118. So half of that is 59. So I'm gonna say 59 of the trials were on this side of the bar, 51 of the trials were on this side of the bar, right? So if I add these together, that'll tell me how many of the trials were more extreme than what we got in our study. Okay, so 260. 260 trials were as or more extreme than our actual experiment difference. But we don't want to know just how many. We want to know the percent of the random data that had that mean difference. And this was 260 out of 1,000, right? So if we divide by 1,000, that's going to give us 0.26, which equals 26%. Okay, you could also just cross off the 0, right? Divide by 10 on both sides, and out of 100, that's the percent, right? 26%. All right, 26% of the data. So 26% of our random trials were sort of more extreme than what happened in there. That's a lot. That means that this number could have easily just happened by chance, not because of the two treatments. So is the difference for the actual data statistically significant? No, because it would have needed to be 5% or below, right? So you need to write that for the explanation. No, because it would have needed to be 5% or below in order to be statistically significant. So this is a third one where really just memorizing the idea is going to get you most of the credit. Because as long as you know the 5%, you could do your math all kinds of wrong here. But if you show me on this one that you understand that this number needs to be less than 5%, then you're going to be able to get this answer correct, even if that answer is wrong. I just need your explanation to match this. If you don't explain it, I can't tell whether you understand the math behind all of it. So make sure you explain your answers, show your work.